More vector calculus. Today we're going to look at the fundamental theorem for line integrals. If you remember in Calc 2 there was a fundamental theorem for calculus, okay, which enabled you to find a definite integral by integrating and putting in the integral limits. So it's similar, okay. The fundamental theorem for line integrals says that suppose C is a piecewise smooth curve with starting point P and ending point Q. Okay, so you have a curve like this, starting point P and Q, and let F be a continuous gradient field. Continuous gradient field. And what do we remember? What the gradient field means? Means there is a particular function F, right, such that the vector field F is its gradient. Then the line integral over C of F dot dr, so this is the line integral of a vector field, is equal to the line integral over C of del F dot dr, because that is what F is. And the fundamental theorem says that this is just F of Q minus F of P. All right? And F is called a potential function. So know that term, because I may ask you to find this. From this formula, there are certain observations we can make. That this integral, to find this line integral of a vector field, it only depends on the values of F at the endpoints. Now remember the last time we looked at the line integrals of vector fields, it was quite a long formula, right? But I'm showing you another formula that you can use. And this is really interesting because it does not depend on the type of path. All it depends on is what is happening at the endpoints. So therefore you can have a path like that. You can have a path doing this. The line integral is the same as long as P and Q are the same points. So we can evaluate the line integral of a conservative vector field. This is very, very important. The only way you can use this formula if the vector field is conservative. What does conservative mean again? There is a potential function F such that the gradient of F is equal to the vector field. So if you have a conservative vector field, the line integral of it is just, you get it by simply knowing the value of F at the endpoints. Okay? Right, that's the first definition. We'll come back to evaluating these line integrals later, but I want to talk about independence of path before we do that. The integral, let me just put a little C below there. That line integral is independent of path if the line integral has the same value along every piecewise smooth path from A to B. Let me show you what I mean by that. So let's say you have points A and B here. And suppose you take the line integral along this path. Let's call it C1. And then you take another path, let's call this C2. And if you find the line integral along each of these paths and they are the same value, right, then this integral is said to be independent of path, or path independent. Okay? And so we say further, so looking at my little drawing here, the line integral is independent of path if the integral over C1 is equal to the integral over C2. F dot dr. Sometimes you don't say the line integral is independent of path. Sometimes you say the vector field is independent. Some books say it differently. Okay, but I'll just say the line integral is independent of path if these two line integrals are the same. Okay, let's move on. Another theorem that's important. The line integral is independent of path. We need a C again, sorry about that. In a region D, if and only if the line integral over C is equal to 0 for every closed path in D. Let me explain what I mean by that. Let me give you a little drawing. Let's do A and B again. And let's put this path, let that be C2, and let this other path be C1. And this entire path all around, okay, is called C. So C is the entire path. And we call it a closed path because it's closed. Okay, it's not, it's bounded all around. Okay? So remember I told you what independent of path is a while ago using C1 and C2. You have the same line integrals. But another definition for independence of path is if the integral over the closed path C has to be 0. And why? So we can look at it this way. The integral y, the integral over the closed path C is equal to, we have two paths. C is made up of two paths, right? It's made up of C1, good, and it's also made up of C2. But look at what happens to C2. C2 is moving the opposite direction. It does not follow C1. Okay? So therefore the line integral over the entire path C, so I don't need an equal sign there. The line integral over the entire path C has to be minus the line integral over C2 because it moves in the opposite direction. But these two integrals are the same. Remember that. For independence of path, they have to be the same. So if they're the same, this is 0. So this is another definition for independence of path. Now I'm going to give you a very important note, and I have put it in bold to show you how important it is, that the line integrals of conservative vector fields are independent of path. That is going to help you quite a lot. And again, let me remind you, I'm going to write it again. What is a conservative vector field F? It is where there is a function F such that the vector field is the gradient. I'm going to say this again and again because we're going to use it throughout this. Okay? All right. Let's go on. Bunch of theorems. Suppose F is a continuous vector field on an open connected region R. What do we mean, by the way? You will see this quite often. What is a connected region? Let me show you what connected means. I think the best way is to illustrate it. So this is connected. If this is R, this is connected. Okay? But if R is made up of two regions like that, that's not connected. Okay? Not connected. Alright, so this theorem only works for connected regions. Alright, so continuing with the theorem. If the line integral over C is path independent, then F has to be conservative. So remember before what I said, the line integrals of conservative vector fields are path independent. Now I'm going in the opposite direction now. If the line integral is path independent, then F has to be conservative. Now, this important theorem will enable us to get some formulas that we'll use for the remainder of this lecture. So what does this mean? Let's go on. So let F be the vector PQ. Okay, and this needs to be a comma, not a full stop. And now let's write out the formula we had for the line integral of a vector field. If you remember from the last time, one way of writing this is the line integral over C of P dx plus Q dy, because I've written down the components of f. Okay, so I'm trying to jog your memory from the last time. Since f is conservative again, what does conservative mean? There exists a potential function f such that del f is equal to the actual vector field. What is the formula for gradient of a vector of a function? It's a vector with the partials. So therefore this vector of the partials is equal to the actual f. If they are equal, we can equate components. That the partial of f with respect to x is p and the partial of f with respect to y is q. What does that mean? Remember, the vector field is continuous. So we can find second partials, and if you remember a long time ago when we did these second partials, fxy and fyx, they are equal if there is continuity. So find the partial of fx with respect to y. So fxy is partial of p with respect to y. fyx is partial of q with respect to x. They are the same, so therefore the partial of p with respect to y is equal to the partial of q with respect to x. Therefore, this brings us to this very important theorem. So after all that I have said, this is what I want to concentrate on. Highlight it, put it on a note sheet for exams. You need to learn this. That's important. So here we go. If you have a vector field with components, why do I have a full stop here again? That is a comma. With components p and q, and you know that vector field is conservative, that's very important, because if it's not conservative, that formula will not work. Okay? So if that vector field is conservative, where p and q have continuous first partials on a domain, then the partial of p with respect to y has to be equal to the partial of q with respect to x. Okay, that's a very important formula or theorem. Let's move on to the converse. The converse theorem. So again, you have the vector field of components function p and q, put a comma between there. So this vector field is on an open, simply connected region D. Again, these words will not mean anything to you if I don't illustrate. What does simply connected mean? It's simple and it's connected. Basically, yeah. Let me see if I can explain it. It has no holes. Let's put it this way. The region has no holes. And it cannot be separated. I think that's a good way of looking at it. It has no holes and it cannot be separated. Okay, so that is what simply connected means. Okay, so you have this vector field on a simply connected region, and you have these two first partials equal to each other. Then f has to be conservative. Now all I need you to know from this simply connected thing, all the regions that we are going to look at for this course are simply connected. We are looking at R2 and R3, okay? We're in 2D and 3D. We are looking at real numbers. They are all simply connected. So basically that's all I want you to know. In all of what I have said so far, what do I want you to know? For any conservative vector field made up of components P and Q, you have this formula holding. It is very important. In R2 and R3, if this formula holds, then the vector field has to be conservative. That's all. So if I ask you to show that a vector field is conservative in R2 or R3, that's all you need to show. Okay? All right, so I've summarized it here for you. The two important things that I have looked at so far are these 2 points. Line integrals of conservative vector fields are independent of path. Why is this so important? If you notice from the last time when you were finding the line integrals of a vector field, it was a little lengthy, right? But if you know that the vector field is conservative, you know that the line integrals are independent of path, so all you need to do is to subtract the value of the function at the endpoints. Makes it a lot easier. All right? And how do you show that a vector field is conservative? Show that these two partials are equal. So in all of this, underline that, it is key, this summary. So I wanted to get to this point. That is what we are going to use now. Okay? So let's do some examples. All right. Example. Determine whether or not F is a conservative vector field. If it is, then we want to find a potential function F such that the vector field is equal to del F. Now, this is going to lead us obviously somewhere along the line to finding the line integral, but I want to take baby steps. Let's first prove that the vector field is conservative. Okay? Then we're going to find the potential function. All right. So what I want us to do is to write out what P is and what Q is. So P would be the first component, e to the x cosine y. Q is the second component, e to the x sine y. Now find the partials. So you find the partial of P with respect to y. What is that partial, anybody? Negative e to the x sine y. Then you find the partial of Q with respect to x. What is that? E to the x sine y. Notice that they are not the same. So the vector field is not conservative. So since these two partials are not equal to each other, F is not conservative. Okay, that's number 1. Let's move on. Number 2. We're doing the same thing. All right, so write down P. Y e to the x plus sine y. Write down Q. E to the x plus x cosine y. Find the partial of P with respect to y. Can you give that to me, please? Very good. E to the x plus cosine y. Partial of Q with respect to x. Can you give that to me too, please? E to the x plus cosine y. They are the same. So therefore F is conservative. So since Py equals Q sub x, F is conservative. So what does that mean? We can find a potential function. All right, let's find the potential function. How are we going to find the potential function? By using the formula that so let's find the potential function F. How are we going to find potential function, we are going to use the fact that del f equals f. But what is del f? Del f is made up of fx and fy, these two partials. Remember that, we're going back. So since these two vectors are the same, we can equate components. And that will enable us to solve for f. Let's compare the first component. So fx must be equal to the first component of capital F, the vector field, y e to the x plus sine y. Now, we'll deal with the second component in a little bit. Or let's write it down. We'll put it on the side there. Fy, the second component, e to the x plus x cosine y. Okay. Let's deal with the first component. What are we going to do with that? Remember what we're trying to find? We're trying to find the potential function f of x, y. Right? So let's use this first equation to find the potential function. Now let me see if you know how to do this. F sub x means we took the partial of f with respect to x, right? So now how do you think we're going to find the actual function f? We're going to integrate. Very good. We're now going to integrate with respect to x. But we're going to do it in such a way that we partially integrate. You with me? Because we partially differentiated before, right? And we held y constant. So now we're going to partially integrate and hold the y constant. So let's do this. When you integrate y e to the x with respect to x, what do you get? How do you integrate e to the x, excuse me? The same thing. Y e to the x. Good. Now, integrate sine y with respect to x. Remember, sine y is a constant. Very good. X sine y. Now, remember when we're integrating, there's a constant, right? Don't put c. Right? C is just a constant. Remember, we're doing partial. We're doing partial differentiation and integration. Y is our constant here, right? So therefore, we are going to put a function of y, because that is our constant. Okay. So we have our function, but we're not done yet. We need to find what that g of y is. How do we do that? That is where you use your second component. So what I'm going to do now, this function that we just found, why don't we find the partial of f with respect to y? Okay, let's find the partial of f with respect to y. Give that to me, please. First term, e to the x. Next term, x cosine y. And then the last one is just g prime of y, right? Good. We have a f sub y on this side. We have an f sub y on this side. Therefore, let me write that in blue. We need to compare these two. When you compare these two, what do you see? That g prime of y is equal to what? 0. Now we in single variable calculus. If g prime of y equals 0, when you integrate, what is g of y? The only thing it could be. Not 1, not 7. Be more general. A constant. Good. So we're done. The potential function f is f of xy equal y e to the x plus x sine of y plus c. Okay, so that's the first step. All right, we'll do some more. Any questions? Yes.
Is there going to be a case where g prime of y is not equal to 0?
Exactly, we'll do that. Oh yes, in many cases like that. Yes, you don't always get just C. Number 3. So remember the steps we are taking? We first have to show that this vector field is conservative, or else we will not find that potential function. Okay? So write down P and write down Q. So P is y cosine x plus 2x e to the y. Q is sine x plus x squared e to the y plus 4. Okay. All right, let's prove. What do we find first? Partial P with respect to y. What is this? Tell me. Cosine x plus, next term, the same thing. Good. Go on the other side. Q sub x, partial Q with respect to x, what's that? Cosine x plus 2x e to the y. Bingo! So F is conservative. They're the same. Okay. Let's find F now. The potential function F. We find the potential function F. And again, I'm not going to write this all the time, okay? Del F equals capital F, right? What is del F? It's made up of the first partials, okay? So take these two partials and put them equal to the components of F. Let's do that. So the partial of F with respect to x is the first component, y cosine x plus 2x e to the y. The partial of F with respect to y is sine x plus x squared e to the y plus 4. Goody. All right. Any questions so far? So take the one on the left and let's find the potential function. At least find some parts of it. So what are we going to do? Partially integrate with respect to x. One person give me the first term. We partially integrate in y cosine x with respect to x. What's that? Y sine x. Good. Just know that when you partially differentiate what you got, you should get what is in f sub x. Okay? Next term. Partially integrate this with respect to x. X squared e to the y. Beautiful. What do we add? G of y, because the y is a constant. Okay? So we have our potential function, but we need to find g of y. So what are we going to do? We need to compare to what we have on the right, right? So now we are going to partially differentiate it with respect to y. Can you give that to me, please? First term, partially differentiate that with respect to y. What's that? Sine x plus the same thing, x squared e to the y, plus g prime y. What do we do? Compare. But when we compare, what do we see? G prime of y is 4. If g prime of y is 4, what is g of y from integration? 4y plus c. Very good. And so our potential function is, let's write it all out. Y sine of x plus x squared e to the y plus 4y plus c. Okay. So let's continue. Let's do this one together. I know I have do here, but let's do it together and then you'll do the second one on your own, okay? All right, so we want to show that this is conservative. So write down P and Q. So P equals natural log of y plus 2xy cubed. Q equals 3x squared y squared plus x over y. Let's find partials. Partial of P with respect to y, 1 over y plus 6xy squared, good. Partial of Q with respect to x is 6xy squared plus 1 over y. They're the same. So F is conservative. Now let's find the potential function F. Any questions so far? So let's write down the partials equal to P and Q. So partial of f with respect to x is equal to P, natural log of y plus 2xy cubed. Partial of f with respect to y is equal to 3x squared y squared plus x over y. Okay, let's take the first one that we wrote, the one on the left. That will enable us to find part of the potential function. So f of xy means we are partially integrating this with respect to x. What do you think that is? X natural log of y plus plus g of y. Excellent. All right, but we need to find g of y. So what do? Partially differentiate with respect to y. Let's do that and tell me what you get. X over y plus 3x squared y squared plus g prime of y. What do? Compare. When we compare, what do we see? G prime of y is equal to what? 0. So what is g of y? Just c. Okay, so write out what f of xy is. The potential function is x natural log of y plus x squared y cubed plus c. Okay? So do this other one on your own and then we will do it together. Any questions? Okay. So P is 2x minus 3y. Q is minus 3x plus 4y minus 8. What's the partial of P with respect to y? No? Negative 3. Partial of Q with respect to x? Minus 3. So conservative. So partial of f with respect to x is 2x minus 3y. With respect to y, it's the same thing. Okay, give me the potential function over here. What did you get here? X squared. When you partially integrated this, what did you get? Minus 3xy. Plus g of y. Okay. Partially differentiate that with respect to y. What do you get? I'm not hearing you. Negative 3x. G prime y. Then you compare when you compare, what do you find? G prime y is 4y minus 8. Good. So what is g of y? 2y squared minus 8y plus c. Great. And so write out your potential function. F of xy is x squared minus 3xy plus 2y squared minus 8y plus c. Okay. So now that we know how to show that a vector field is conservative, and if it is conservative, we can find the potential function. Now we can evaluate a conservative vector, the line integral of a conservative vector field by just evaluating the potential function at the endpoints. So we're going to do the same thing again, but the last step is just to evaluate the line integral. Okay, so I've guided you. Find a potential function f such that the vector field f is equal to the gradient of the potential function, what we have been doing all along. Hence, evaluate the line integral, put your little c below here, along the given curve c. And how are we going to do that? We are going to use the fundamental theorem of calculus. Alright, so let's start. Before we find the potential function, we have to show that the vector field is conservative. So do the same thing. For the vector field f, write down what p is. P is xy squared. Q is x squared y. That's a Q. Partial of p with respect to y, 2xy. Partial q with respect to x, 2xy. So this implies f is conservative. Good. Let's find the potential function. Set up your two equations with the partials. So f partial x is xy squared. Partial of y, f with respect to y is x squared y. Now, on the left, let's find the potential function f of xy by partially integrating with respect to x. So if you integrate x there, you're going to get a half x squared y squared, but you need to add g of y. partially differentiate with respect to y. So fy is x squared y plus g of y. Compare. So, oh, thank you. G prime of y. Thank you very much. Compare. G prime of y is 0. So this implies that g of y is c. So the potential function f of xy is a half x squared y squared, well, plus c. Good. Now look at the path. So we've done the first part. We now need to evaluate the line integral over the path. Now that's the path c is this r of t thing here. Okay? And you are told that t goes from 0 to 1. Why did they give you these values for t? To find the starting point and the end point. So how are we going to find the starting point? Plug in t equals 0 into the path. That will give you the starting point. And to find the ending point, put 1 into the path. Okay? So c is the path r of t. So the starting point is, we are going to put 0, right, into r. So we are going to find r of 0 and write it down as a point. So where's my r? So when you put 0 here into the first component, I think you'll get 0. And then when you put 0 into the second component, the t plus cosine a half pi t, well, that's 0, but this is cosine of 0, which is 1. So the first point is 0, 1. Now let's take the second point, the end point. We want r of 1. The end point is r of 1. What do we have here? Put 1. So that's a 1 plus sine of a half pi. Sine of pi on 2 is 1. So 1 plus 1 is 2. And then the other one is 1 plus cosine of a half pi is 0. So it's 2, 1. Okay? So now we are going to find the line integral over c of f dot dr is equal to, what does the fundamental theorem of line integrals say? Take the potential function and evaluate it at the endpoints. It's just like the fundamental theorem of calculus. When you're integrating, right, you integrate and you plug in the limits, right? Now in this case we will not need the constant c. So this is what we're going to do. The potential function is a half x squared y squared. We are going to evaluate it at the end point. The first point is 0, 1. The end point is 2, 1. That's what we're doing. So plug that in. So put 2, 1 into here. We get a half times 4 times 1 minus, put 0, 1 into here. That's 0. This ends up being 2. Okay. Questions so far? Okay, next one. Let's do another one. So we have the vector field, and C is that arc. I think I wanted to say the arc. I don't know where that came from. The arc. C is the arc of the parabola y equals 2x squared from negative 1, 2 to 2, 8. So we already have the points, okay? So we don't need to evaluate what the points are. So now, let's show that this vector field is conservative. Let's find the potential function. 3 steps. Show it's conservative. Find the potential function. And finally, evaluate the potential function at the points. Let's go. Conservative. Write down your P and your Q. P is x squared. Q is y squared. Partial of P with respect to y, tell me. 0. Partial of Q with respect to x, tell me. 0. So this implies F is conservative. Next step. Find the potential function. Okay, so let's write that. Find F. How are we going to find F? Write out your partials. Partial of f with respect to x is just x squared. Partial of f with respect to y is just y squared. Okay, let's go. Find f of xy. So partially integrate x squared with respect to x. What's that? 1/3 x cubed. And what do we add to that? G of y. Find partial of f with respect to y. What is that? Just g prime of y, right? Because the first one is x. Now what? Compare. When we compare, what do we get? G prime of y is y squared. And a g prime of y is y squared. What is g of y? Say that again. 1/3 y cubed plus c. Good. So your potential function, f of xy, equals 1/3 x cubed plus 1/3 y cubed plus c. Last step. Find the line integral over C of f dot dr. Means we are going to evaluate that function at the endpoints. So don't worry about the C. So this is 1/3 x cubed plus 1/3 y cubed evaluated at. What's the starting point? -1, 2. And the endpoint, please? 2, 8. Okay, plug that in. So you first put 2, 8 in there. 2, that's 8 over 3 plus 8 cubed over 3 minus, put the other point in there, that's -1/3 plus 8 over 3. And this ends up being 171. No, a good point. We're not doing anything with the parabola. Why? Because we know it's a conservative vector field, so we don't have to do anything with it. We already have the end and the end point and the starting points. You mean I didn't give you any to do?
No.
That was supposed to be do.
It's okay.
And I did it. Why did you tell me?
We thought you were just being nice.
I wanted you to do that. But did you, is that okay? You understand this? Okay. Ay, ay, ay. Okay. Green's theorem. Green's theorem also enables us to find the line integral of a vector field. But there's one, and it makes it really easy. But there's one condition. The line integral, the path that we are finding the line integral over has to be closed. If it's not closed, you cannot use Green's theorem. Okay? And what is beautiful is that how does it relates a line integral over the closed curve with a double integral over the region. So this is what is happening. So this is your path. It has to be closed. C, and this is your region R. So it relates the line integral over C with the double integral over the region R. But there's one condition. The orientation, remember you always have arrows on the path, right? The orientation has to be important. We are looking at a positive orientation, which is counterclockwise. So if the orientation of the path you're looking at is in a clockwise direction, you'll have to negate everything. Okay, put a negative on everything. All right. What is Green's theorem? Suppose C is a positively oriented, piecewise, smooth, simple, closed curve. What do we mean? By the way, simple, let me see, what's the easier? Simple is not the English language definition of simple. The mathematical definition of simple is, okay, let me tell you what not simple is. Okay, simple is a curve with no loops. So for example, this is not simple. Okay? All right. Good. So you have all of these things happening to C, and R is the region bounded by C. Then the line integral over C. So it's I'm going to underline close because this is just, it has to be closed. Do not use Green's theorem if the curve is not closed. It will not work. It doesn't hold. Okay? So the line integral over C of this vector field, which is the same thing as, you need to write it like that, is equal to the double integral over R of the difference between these two partials. Done. Okay? Now, by the way, in some books, you will see this notation. They can use this notation to show you that you are using Green's theorem is over closed curve. They will put it like this for you. You'll see this in some books, and they put a little arrow. So you can see this as well. Okay, so if you see this, don't get confused. It just means the same thing. Okay? Okay, let's do some examples. Green's theorem is quite easy because it's just a double integral, something you've done before. Okay? So, let's find this. So you have this vector field. Use Green's theorem to find the integral over C. This line integral of the vector field, where C is the rectangle with vertices 3, 0, 3, 5, negative 1, 5, negative 1, 0, traversed in that order. Now, let me just write Green's theorem here again, so we don't have to go back and forth. Double integral over R of partial of Q with respect to X minus partial of P with respect to Y dE. Okay? Now the first thing I want you to do is to draw this rectangle, please. So we want 3, 0. We want 3, 5. We want negative 1, 5. And we want negative 1, 0. And put the traversal, put the arrows that you need to put, so it's traversed in that order. So from 3, 0 to this, to that, to that, to that. So you know that this is counterclockwise, and this is your R in the center. Okay? Alright, so what I would want you to do, it's over a rectangle, so the integral is going to be quite easy. Let us find these partials, okay, and subtract them. First of all, you will need to write down what P and Q are. So P is equal to sine x. Q is equal to x plus y. Find the partial of P with respect to y. What's that? 0, yeah. What's the partial of Q with respect to x? 1. So, the difference, partial with respect to x minus the partial of P with respect to y is just 1. Okay? So what we are finding, therefore, is the double integral over R of 1. What? Now, that is where you need to remember some formulas I've given you. Use some shortcuts when you can. You find the double integral, you know, putting in your limits and so on, but what is this definition? What is the double integral of 1? Area. So this is really the area of R. And we know how to find the area of a rectangle, right? Saves time. So what is that? What's the length? I think this is a 5. 5 times 4, that's 20. Done. We did not even have to do any integration. Isn't that lovely?
I like that.
Yeah, I love it too. Yes?
I could solve the area rectangles all day.
Of course, that can be allowed in the test, and I would advise you to do that. If you see something like that, don't waste your time and, you know, integrate. Next one. Put down Green's theorem again here, okay? Put your little C below here for me. F dot dr is the double integral over R of the partial of Q with respect to X minus the partial of P with respect to Y dA. Okay? Alright, what I want to do is to draw this triangle, please. So we're going from 0, 0 to 0, 4 to 2, 0 and back to 0. Okay, and that is also counterclockwise, is it? Okay. Okay, so let's go. Let's find that integrand first. So let's write down P and Q. Let's find the partials and let's subtract. So P, and of course, let me put R in the center there because this is R. Whoops. Okay. Okay, partial time. P is equal to y cosine x minus xy sine x. Q is equal to xy plus x cosine x. Okay, that's going to be a little rough here. Okay. Pardon me?
0, 4. 0 on X, 4 on Y.
Did I do the wrong thing?
Looks like it.
I did, you know. I did 4, 0 instead of 0, 4, right? Thank you. Yes. So it's going to be very good. Okay, let's, come on. Let's just start over. Thanks. Zero, 0, 0, 4, and 2, 0. So we are going like this then, clockwise, right? That's what we're doing, right? So that's in the wrong direction. Good. So we'll have to put a minus outside this, okay? All right. Okay, what were we doing now? Let's find the partials. So the partial of p with respect to y is cosine x minus x sine x. Partial of q with respect to x is y plus. Now this here is a product, so we have to use a product rule. So differentiate x, that's a 1 times cosine x. X times minus sine x, so that's minus x sine x. Okay. Let's subtract now. Partial of q with respect to x minus partial of p with respect to y is y plus cosine x minus x sine x minus cosine x minus x sine x. I'm missing a y, right? No space. No, what am I doing? I am a little tired tonight. I'm right, right? When you subtract, you get y. I love it when you subtract and you get something so easy to integrate. Eh? You love it too, don't you?
I'm guessing that doesn't happen very often.
Yeah. Green theorem makes things beautiful and simple. I love green. Okay, let's do this. So what are we integrating? We're finding the double integral over r of y dA. Now, please don't tell me that is the area. Okay? You have to go the long route. You have no choice. This is your r inside here. Remember how we find the double integral of this region? Either vertically or horizontally simple. You with me? Let's make it vertical. So let's writing our limits. Let me put this a little lower because that might, or more on this side. So we want y dy dx. Our x limits are 0 to 2. Now the y limits, we will need to find the equation of this line here. And when you find the equation, you get y equals 4 minus 2x. And so the y limits go from 0 to 4 minus 2x. And this ends up being, let's just do this. 0 to 2, integrate with respect to y, that's y squared over 2, from y equals 0 to y equals 4 minus 2x dx, which is equal to 0 to 2 of 4 minus 2x all squared over 2 dx. Oh ho, what did we forget? What did we forget? The negative. So just sneaking a negative outside there.
Like it never met.
And this is equal to this is equal to negative 16 over 3. Okay. Okay. Number 3. Let's do this together. Put your little c below that integral for me, please. Here. Okay, so use Green's theorem to find this, where C is the rectangle with vertices. Okay, so draw your rectangle. Zero, zero. Now, you know when they don't tell you anything about the traversal? Assume it is counterclockwise. Okay? So 0, 0, 3, 0, 3, 1, 0, 1. And just assume it is counterclockwise. Okay, go ahead. You've drawn it? Now we're going to use Green's theorem. What do you do now? Tell me. Write down P and Q. Do that. No, because you don't know. You cannot just keep to find the area because you don't know what the integrand is going to be. The only reason we were able to find area is because when we subtracted the two partials, we got 1. Okay? You found the partials? What's the first one? X, yes. And what's the second one? 2x. Okay. What's the next step? QX minus PY. What's that? X. So now you're integrating. It's a double integral over x. Now here you can make that horizontally simple or vertically simple, and you have to integrate here. You have no choice, okay? Did you make it dx dy or dy dx? Dy dx, no problem. And make sure you put the limits in the right place. What's the outer limits? 0 to 3 and the innermost. Okay, go for it. What did you get? 9/2. Is that okay? Okay. I want to do this question because sometimes, and again, don't think that because we finished with the last chapter dealing with polar coordinates and spherical and so on that you're not going to use it again. Sometimes when you are doing a question of Green's theorem and you set up your double integral, it would be a lot easier to use polar, especially if it's over a circle. Now, I want to make this point before I continue. All these integrals we are finding, you could have used the formula that I taught you in the last lecture, you know. When I first introduced line integrals over vector fields with you, you can use that formula for all the questions we have done here, but it's going to take you a little longer. So that is why it's good to know some of these theorems. Okay, so let's do this. Use Green's theorem to find this over C. Put your little C of y squared dx plus 2x minus 3y dy. And C is the circle x squared plus y squared equals 9. Okay, we don't have to draw the circle. We know what it looks like. Let's write down our P and our Q. P is y squared. Q is 2x minus 3y. P with respect to y is 2y. Q with respect to x is 2. So Q sub x minus P sub y is 2 minus 2y. Okay? So what you are finding is the double integral over the circle of 2 minus 2y dA. So because it is over a circle, what do we convert to? Polar coordinates. It's going to be easier for you. Okay? So what is our integrand going to be? 2 minus 2, our y is r sine theta. We multiply by r dr d theta. What are our limits for r? 0 to 3 for theta, 0 to 2 pi. Okay. Equals. Now let's distribute that. 0 to 2 pi, 0 to 3, 2r minus 2r squared sine theta, dr d theta. Okay, now let's integrate with respect to r. 0 to 2 pi, this is r squared minus 2/3 r cubed sine theta. R goes from 0 to 3 d theta. When you substitute, you get 0 to 2 pi, and this is 9 minus 18 sine theta d theta. Integrate 9 theta plus 18 cosine theta, 0 to 2 pi, and this ends up being 18 pi. Okay. Okay, last one. Green's theorem also enables us to find the area of a simple closed curve. And we have a bunch of formulas that we can use here. So the area, I'll put your little C's below here, can be either of these. You can use either of them. Okay? Alright, so today I'm going to use the last formula. I'm going to use the line integral over C of x dy. Any one would work. Okay. Find the area of the circle bounded by x equals a cosine t, y equals a sine t, and t goes from 0 to 2 pi. Okay, so x equals a cosine t, y equals a sine t. Now look at what, this is what we're going to use, the last one, okay? We know what x is. dy we have to calculate. What is going to happen is that everything is going to be in terms of t. So find dy from y equals a sine t. So just differentiate. This is just single variable calculus now. Okay? So dy equals a cosine t dt. Okay, so now let's plug it in. So the area, which is the line integral over c of x dy, is equal to, so put everything in. X is a cosine t, y dy, sorry, is a cosine t dt. What are the limits? 0 to 2 pi, which works out to be 0 to 2 pi of a squared cosine squared t dt, which works out to be pi a squared on your calculator. Now this makes sense. Do you know why? Look at these two equations, x equals a cosine t, y equals a sine t. That defines what? A circle. Radius a. So the area is pi a squared. Any questions? We're done.